So you can see my screen now. I have to
yes.
full screen. Is it better now?
Yes, I think that's okay.
And you can see my cursor, right?
Yes.
Okay, and who is the chairman of? So when should I start?
I think you can chair yourself.
Okay, okay, so let me start. Okay, thank you very much for giving me a chance to speak. I want to talk about symmetries at null boundaries and present a few concrete examples, 2- and 3-dimensional examples. This is mostly based on a work published last year in collaboration with Hamed Adami, H.Yavartanoo, Tagilu, and Celine Zickel. I don't need to say much about motivations of this work. This has been discussed extensively in this conference. So let me just, instead of saying any words about motivation, let me just start boring you with some technical details of a few concrete examples of symmetry analysis for different gravitational theories. The simplest theory, the simplest dimensions, the lowest dimension that I can imagine gravity is 1-dimensional space, or let's say 2-dimensional space-time. The Einstein theory in 2-dimensional space-time is topological theory. So to get something non-trivial, either we should go to the higher derivative or adding some other fields and couple these other fields non-minimally to the gravity. So for simplest example, let's say we have one scalar field and coupled to the gravity non-minimally, and assume this scalar field has a potential. Even though it is very simple examples, but it includes many interesting models that has been discussed for various reasons last several years, including the compactification of higher dimensional gravitational theory with spherical symmetries. It is easy to show that with a redefinition of the metric, we can always set lambda to 0, even though the scalar field doesn't have a dynamical part after this rescaling, but as it is coupled non-trivially to the scalar curvature, it has a dynamics. So we can try to solve equation of motion for a given scalar potential. The equation of motion given by varying the action with respect to a scalar field and the metric are given by these two equations. Now in this geometry, we want to consider a codimension 1 null hypersurface. So here means null line, a generic equation which gives this null hypersurface can be written in this way. R, let me take R and V to be the coordinate of that 2-dimensional space-time, and we want to take R equals 0 to be the position of this null surface. For a given potential, I can solve the equation of motion, but I don't really need the full solution, as I'm only interested in analyzing the charges near this null hypersurface. So what I'm interested is the form of the metric near R equals 0, and also a scalar field near R equals 0. Using diffeomorphism, I can always set GRR to be 0 and the component RV to be only a function of V. Then assuming R equals 0 is a null surface tells me that if I expand GVV as a function of R, it should start with power R. Now I can take these ansatz and put in the equation of motion. up to the first order in R, the only non-trivial equations I get is this one, which I can assume, which I can consider it as an algebraic equation for F0. So the full solutions, the solutions phase space at this order is given by two functions, phi 0 and 8. If we can go to the higher order and try to solve order by order equations, and we find that knowing phi 0 and eta, we can construct the whole solution, but we don't really need that. All we are interested in is this metric and a scalar field near r equals 0. And this gives us the solution phase space. These two functions of V determine the solution phase space. Now we are looking for diffeomorphism which preserve the form of this metric and also keep the position of the null surface intact. And, such a diffeomorphism are given by following vector field, which I have written its expansion up to the R squared terms. So here T and W are two arbitrary functions of V. This diffeomorphism forms an algebra, which is given by these relations. Assuming T and V are meromorphic functions, it is we can expand them in an appropriate base. So let's take Tn and Wn be bases of T and W. Now the algebra of the algebra of null boundary symmetries takes this simple form, which is the BMS algebra. This is also it is also interesting to note that this is a sum of one-dimensional diffeomorphism and Weil algebra. The effect of this diffeomorphism on different component of the metric can be given by these two equations, and we can eventually look at the charges, conserved charges corresponding to this diffeomorphism. Going through the the analysis of the conserved charges, this can be obtained by this expression. It is important to note that when phi is a constant, this expression vanishes. So, to get non-zero charges, we need a non-constant phi, as it is expected in 2 dimensions, as the 2-dimensional Einstein theory is topological. It's also important to note that this formalism doesn't give us the charge, it gives the variation of the charge, variation of the phase space. So it gives the delta of the charges. And if we use the expression for the metric we had and calculate the charge at r equals 0, what we get is this expression. And it is clear that if I take W and T to be field independent, then what appears on the right-hand side of this equation is not really a delta of something. And that's why I write it as a delta S slash. So this delta S slash is W delta phi 0 and plus this expression, which gamma is a function defined in this way. So the appearance of the charges which are not integrable are known from a long time ago in analyzing, for example, the asymptotic symmetry group of ADS gravity by these authors. And it has been discussed how we can deal with these non-integrable charges. For example, in the work of Barnish and Trozar, they argued that we can always separate, when we have a non-integrable charge, we can always separate the integrable part and some remaining part, which is a flux, and using a modified bracket, which formally defines in this way, although practically what we calculate is not this part, but formally it defines in this way. And in this definition, as you can see, there is an ambiguity. We can add some arbitrary functions to the Q part, to the integrable part, and subtract the delta of it from the flux part. But using this modified bracket definition, we can fix this ambiguity. And up to the a possible central charge, which for this particular example we have, if we go through the analysis is 0, we can find the flux and the charges. But what I'm going to tell you here is indeed another way to look at this non-integrability of the charges. Assume that we consider a change of a slice by taking a linear combination of symmetry generator, which in our case were W and T, with a possible field-dependent coefficient. So let me define W hat and T hat in this way, and assuming this W hat and T hat, these new generators, are field independent. As we are dealing with field-dependent generators, we should use the modified bracket instead of adjusted bracket instead of the normal the brackets of two vectors, and using that with the new generators W hat and T hat, we get the following algebra. It would be more appropriate if I define new functions instead of phi 0 and eta. If I define P, which defined in this way for arbitrary real number S, I define P to be this function, or for S equals 0, I define P to be this. Then the variation of charge in this new slice is obviously integrable, as I assume W hat and T hat are field independent. So it is like taking the steps on the phasor space, which are, in this case, are field independent, independent of the position of on the phasor space. And it was indeed expected, as in the absence of propagating degrees of freedom, physically we expect that we can always find the slice which the flux vanishes. The transformation law for these new fields can be for S equals 0 and S non-zero are given by this one. And it is also important to note that for a generic non-zero S, we can always obtain PS as a function of P0. So we can always obtain PS from the P0. And the charge algebra for P0 for S equals 0 is just the simple Heisenberg algebra. So a few comments before going further. So the null boundary in this two-dimensional example is a line which is parameterized by V, and the boundary phasor space or boundary phasor space in these examples are given by two functions of V, phi 0 and P0. That's our the boundary degrees of freedom of one-dimensional, can be assumed as a boundary degrees of freedom of one-dimensional particle. And the V dependence of the charges are not fixed in our analysis. Indeed, this is the result that we did not fix the boundary condition on that null surface. So the boundary Hamiltonian, or let's say the generator of translation along the V direction, is not determined through this analysis, or we have the most general possibilities here. Now, once in an integrable, we are in an integrable slice, we can ask the question, can we still make a further change of a slice and get integrable charges? And we should also ask, is it always possible to make a set of given non-integrable charges integrable by this trick, means by going by using field-dependent change of a slice? And if it is not the case, when does the integrable basis exist? In next few examples, I will show you, I will try to answer the first question. The examples which include the second question will be discussed in the other talks in this conference. So in general, consider integrable charge which generated by symmetry generators, mu I. In general, d-dimensional case, I can write the variation of charges in this way. Now, if I assume that delta QIs are integrable, then I should take mu i's to be field independent functions, means the variation over the phase space of these mu i's should be 0. The charge variation is integrable on the phase space. Now I can perform integration over phase space. Please do not confuse it with this integral, which is on space time. I can integrate over phase space to determine the charges. So the conserved charges can be written this way. Now consider a generic change of a slice, means going from this set of charges Qi to, let's say, Q tilde i's, where these Q tilde i's are general functions of Qi's and all possible derivatives of the Qi's. And we want to impose the condition that these new charges are integrable. That means that if I write this charges in the new basis, in the new slice, then this new chemical potential should be related to the old chemical potential in this way. Now, also the charge variation delta Q is the same in these different slices, but the result of integrating over the phase space integrated charges Q is not necessarily the same in two different slices. Now, if I write this delta Q as this matrix form, introducing this matrix Pij times delta Q, where Pij are some functions and some derivatives acting on delta Q. But in general, Pij can be written as Pij A1 to AP and some different derivatives from zero derivatives means functions up to some derivatives. Then the mu i's can be related to mu tildes if this new base are integrable in this form. Now, the Poisson bracket of the charges in, if I write the Poisson bracket of the charges in the original slice in this generic form, then after change of a slice, the bracket can be written in this way. Now, it is clear that the right-hand side of this equation is not necessarily of the form of Fijk Qk plus some possible central charge. So it is not clear that on the general change of a slice, we can close the algebra. In other words, the closure of algebra impose some constraint on Pij's or the generic way we go from one integrable base to one integrable slice to another integrable slice. Also, the Jacobi identity in the old, the newer slice can be written in the form of some matrices times the Jacobi identity in the older slice. So in order to get the Jacobi identity satisfied in the newer slice, we get again some constraint on the possibilities of form of PIJs. So it is possible to find an integrable slice. So we should ask, is it possible to find an integrable slice where the charges, the charge algebra is a Lie algebra or some possible extension of Lie algebras up to some central charge? That's one important question we should ask ourselves. The other question we should ask here is, are there other possible changeover slices that take the integrable basis, the integrable algebra to another algebra? And also we should ask if there are other integrable charge algebra. For example, if the answer of the previous question is positive, are there Lie algebra among them or not? For this simple two-dimensional examples, we have already seen that there are infinitely many different integrable bases indeed exist for each given real number s. I give you one such an example in which the algebra of charges is a Lie algebra. Now we can ask whether this S family of algebra is unique. It's not difficult to answer this question. For example, starting from S equals 0 and writing the algebra and considering the general changeover slice given by this matrix Pij, which in this simple two-dimensional example, it's just very simple form. So that the commutation, the Poisson bracket of two charges in the new slice, therefore takes this simple form. So we have two pi's here and an epsilon here. So it is just determinant of P appears here. Now the condition to having a Lie algebra gives us a constraint on this determinant. So it tells us that this determinant is a linear function of Qi's. Now, the charge algebra, if I take the determinant as the linear function of Q's, can be written, therefore, in this new slice, can be written in these forms. Now, if I assume alpha I were 0 for that general Pij, so this is nothing but a generic canonical transformation on two-dimensional phase space. So we go from one Heisenberg to another with a different central charge. For non-zero alpha I, we can always rotate the basis of two-dimensional phase space to set one of alphas equals 0, and let me call the other alphas to be S. Then the Poisson bracket of charges in the new slice will take this form, which is indeed if gamma over 0 was nothing but the one of S member of our S family. So this is nothing but the centrally extended of our S families. In other words, in two-dimensional case, our earlier construction already covers the most general integrable slice up to a possible central term in the gamma. Now we can go to higher dimensions. We can go, for example, to 3 dimensions. 3-dimensional gravity is interesting. It is still simple enough to solve the equation of motion analytically, but it is yet non-trivial enough to have some interesting solution there. For example, we can have a black hole solution there. So this is the next interesting example to analyze. So let's consider three-dimensional gravity coupled three-dimensional Einstein gravity with some cosmological constant. The equation of motion, this one. Once again, we can write an appropriate answers for the metric. We use diffeomorphism, with some of diffeomorphism to set, for example, GRR equals 0 and GVR to be a function of only V and phi, independent of R. So we can take this one as an answer for the metric. In 3 dimensions, I can solve the equation of motion analytically for this given answers. But again, I don't need the explicit form of these functions. All I need is their near R equals 0 behavior to analyze the charges of this null hypersurface. So all I need is their behavior near R equals 0. I assume they are analytic functions near at R equals 0. Indeed, I can check that this is not a restrictive assumptions if I from the solution, from the generic solution, I can check that indeed with this given answers, the metric components are analytic functions of R at R equals 0. So I assume they have these expansions. All I need are first few terms in these expansions. Taking R equals 0 to be a null hypersurface, related F0, this capital F0 to the small f0 and omega. To get non-singular solution, I also assume that omega is non-zero. So up to linear terms in R, I have 6 functions here, 1 here, but there is one relation among them. So I have 6 functions here. And equations of motions relate some of these functions, more precisely, can determine 3 of these functions. So there are 3 equations of motions at that order, which can be combined and massaged to this to write as form of these 3 simple equations, where these functions epsilon and capital gamma and chi are defined in this way. So in this form, there are some algebraic and some first rank differential equations for these new defined functions. Now, once again, I'm looking for the diffeomorphism which preserve the form of the metric and also keep R equals 0 to be a null surface. Such a diffeomorphism are generated by following vector fields, which has following components up to the R squared term. I have written their expressions. Again, I don't need the full expressions. All I need is first few terms in this expression. So this vector fields are given by 3 arbitrary functions of v and phi, which are t, w, and y's. So t, w, and y's are arbitrary functions of v and phi here. The null boundary symmetry generating vector fields forms this algebra for us, which is indeed is sum of diffeomorphism on null cylinder and while on the same null cylinder, which is parameterized by v and phi. Where t and y here are the generators of diffeomorphism on the null cylinder, and w is the generator of while on this null cylinder. Now, on the transformation generated by these vector fields, different components of the metric, or let's say these new functions which we introduced, are transform in this way. Once again, going through the world analysis to read the surface charges, we can get this expression for surface charges, which once again, we see that what we get for the variation of charges is not integrable. Means what appears on the right-hand side is not really, in particular, this term is not really delta of something. So this delta slash of A is defined to be this one, which is obviously is not delta of any functions. Now, again, we can take a state, or let's say field dependent transformation. So we introduce this W hat, Y hat, and T hat, assuming these are field independent, and also introduce this sigma S. It's useful to introduce this sigma S this function. Now, in this new slice, which is given by W hat, Y hat, and T hat, the charges are integrable. If I assume W hat and Y hat, T hat are field independent, means delta of W hat, delta of Y hat, and delta of T hat are vanished. Where here, this delta PS is defined to be 1 over S sigma S for S non-zero and minus ln of sigma, this must be 0, sigma 0 for S equals 0. Now, the charges are, as I said, the charges are integrable if we assume these are field independent. Now, the equation of motion for this new introduced function P is given by this one, and along with two other equations of motion, so for the epsilon, gamma, and the others, we can solve these three equations to determine the other component of the metric and write everything as functions of omega, epsilon, and P. So among these 6 functions we have, we can solve 3 of them using these 3 components of the equations of motions, and write everything as in terms of gamma, omega, P, and epsilon, which are 2 functions of V and phi. In solving these equations, we get some integral constant, well, here V-dependent integral constant, but as they don't appear in the expression of the charges, it means that we can always find some trivial diffeomorphism to set them to 0. So the solution phase space can be characterized by these 3 codimension 1 functions on the null hypersurface. Now, the symmetry generators form these algebras, and the variation of the charges under the diffeomorphism can be also obtained. Now, the algebra of charges in this new base is given by this one, and the charges, these charges which are V and phi dependent form this algebra. This algebra would be more transparent if I it's easier to look if I find the Fourier transformation of this. If I write the charges in terms of their Fourier transformation, and upon the quantization, means replacing a Poisson bracket with Dirac bracket, the above algebra takes this rather familiar form. So this algebra consists with algebra, which is spanned by Y, and it's a semi-direct sum with the algebra generated by T, this super translation, which has a conformal weight 2s, and also a current given by W with conformal weight 1. And these two super translations commute among each other for s equal 0. Just like two-dimensional case, for generic S, the generic S can be obtained by obtained from s equals 0 from this form. It is also interesting to note that the cosmological constant does not appear in the final expression for the charges and algebras, and that's somehow expected as our analysis is local near the null surface, and it should be blind to the global structure of the space-time. So we expect lambda does not appear neither in the expression for charge nor their algebra. The form of the metric near r equal 0 null surface may be also viewed as a near horizon metric, where in this case omega, which would be the area, or more precisely area density of the bifurcate horizon, would be the entropy, or more precisely entropy density of that black hole solution. A few comments before going further. Let me write the form of the algebra again for case s equals 0. And so as you see that in this case, omega and p forms a Heisenberg algebra, and one can treat the p0 as a conjugate momentum of the field omega. And these commutation relations may be viewed as equal time canonical commutation relation of a two-dimensional field theories, which is the theory living on the null hypersurface. Now we can ask the same question we try to answer in two-dimensional case. So we can look at the change over slices and go to the other slices. So starting from s equal 0, it would be more useful if I define new functions s, so keeping phi 0 and p 0, and defining s, and replacing epsilon by this new s. Now, to keep the slice integrable, we should also transform the symmetry generators properly. So for this transformation of the I introduced here, I should transfer the y, w, and t in this way. So I don't need to change y, but w and t should be also translated in order to keep the change of slices integrable. And then in this new slice, in this tilde slice, the transformation laws for the charges are given by this, and the Poisson bracket of the charges will replaced by these new equations, which is just sum of the Heisenberg and diffeomorphism on S1. In terms of their Fourier modes, this algebra takes this simple form. Now we can search for the further integrable Lie algebra. So in the other slices, it would be more useful if we introduce two new currents, J hat, J plus, and J minus, the combination of omega and p in this form. and also introducing the new chemical potentials, this epsilon plus and epsilon minus from W tilde and T tilde. And in this new slice, the charges are integrable. And the transformation laws of charges can be written in this form. And the charge algebra will be two current algebras. So we can ask, do we have other slices, change over slices, which keeps us in the Lie algebras? Instead of trying to answer this in generic form, let me show you two possible and interesting examples of such transformation. So as the first example, let's introduce L plus and L minus from J plus, J minus, and S in this way. So L plus and L minus are has this quadratic form of J and plus its derivative. And also introduce epsilon plus and epsilon minus. Then in this new slice, the charges are integrable, and the variation of the new generators are taking this form. And the algebra of the charges in this new slice will take this form, which are direct sum of two Virasorows with central charge related to that arbitrary number beta, which we define to construct L plus and L minus. So we get arbitrary central charges here. As the other example, let me combine these currents to make two new currents, K and J, and define L and M to be following combination of J and K. Now, with this chemical potential epsilon L, epsilon M, which are related to epsilon plus and epsilon minus this way, the charges are integrable, and the algebra of charges takes this form, which is nothing but a width plus centrally extended BMS algebra with this arbitrary central charges. One can argue that this is the only possibilities of getting Lie algebras using this change over slices. So starting with two current J plus, J minus, or equivalently J and K, if the charge redefinition involves the higher power of the current, higher than 2, then one can argue that the algebra will not close. One can also show that having more than one derivative on currents will not the closed algebra. So we have lots of restrictions. We restrict to the linear or quadratic power of currents, and also the first derivative of it. So we are restricted to some sort of twisted Sugawara types possibilities. In this form, the width part of the algebra is not deformed, so it is as it is the stable part of the algebra. So let me, as my time is almost finished, let me just say a few words for conclusion. So in this work, we studied asymptotic symmetry near the null boundary in a few examples in two-dimensional gravity and three-dimensional case. In our analysis, we did not impose any specific boundary condition. Not imposing any boundary condition means that the theory which governed by boundary degrees of freedom is not specified, and their V-dependent remains arbitrary. We also analyze the role of the field dependent through the change of a slice. As our analysis explicitly demonstrated, the field dependence does not necessarily influence the number of boundary degrees of freedom. We established that in two and three-dimensional examples, there exists a slice in which the charges are integrable. Means the non-integrability of charges may be removed by working in a particular state or field-dependent slice. We discussed that the integrable slice is not unique. In two-dimensional examples, we show how to find all of them, infinitely many of them. We wrote the charges in different slices and computed their algebra. In two-dimensional case, we exhausted all such integrable Lie algebras slices, and in three-dimensional case, we present some arguments what is this exhaustive slice are expected to be. So let me stop here by showing you this last slide, and if there is any question, please.
What's the physics of change of slicing? What happens physically when we change the slicing? Or does any specific slicing has a physical meaning, or maybe we need to work with slicing variant quantities? Can you comment on this?
Well, that's a very important question indeed. As I said, we didn't impose any specific boundary condition on our fields in near the null hypersurface. So different slices might related to different the boundary theories. So going from one slice to the other might be related to going from one to the other theory. That's, did I answer your question?
So by theory here, you mean the boundary theory, not the boundary.
The theory living on, yes, the null surface.
Okay. So basically what you're saying is that in this analysis, the boundary theory is not specified, but it is possible to specify it, but can we do all this change of slicings, and as you did in the maximal phase space, and specify also the dynamics? Or
well, specifying dynamics may restrict us to may restrict us, so we may lose some of these charges. So this is what we present here was very generic without referring to any specifying any boundary condition. So Did I answer your question?
Yes, yes. Thank you.
Is there other question? I think here. Okay, if there is no question, so let me stop sharing my screen. Stop sharing.
It's on top of the page. View options.
Oh, okay.
Okay.
Stop sharing.
Okay.